So let's talk about reflection and refraction. These are two things that light will do when it hits a boundary between two media. Now, we all know that the speed of light in a vacuum is the same. It doesn't depend on what type of light you're talking about. But if I have light traveling through a transparent medium like glass or water or benzene or something like that, then it's going to interact with the medium. It's going to interact with the molecules of water, and that's going to slow it down. So it turns out, for example, that light moves a lot slower through diamond than it does through water. So what happens is when light hits a boundary between two media that support different light speeds, something happens at the boundary. So we have a light ray coming in like that, and then it's going to split into two rays. Part of it will be reflected off of the boundary between the two media, and part of it will be refracted. It will be transmitted into the new medium. Okay? So part gets reflected, part gets refracted. Now, in order to mathematically describe what happens during this reflection process and this refraction process, we're going to measure the angle at which it hits the surface, and we're going to measure that off of this line that's perpendicular to the boundary. So we draw what we call a normal line. Normal in physics and also in mathematics means perpendicular. So we draw this perpendicular normal line, and then we measure the so-called angle of incidence, which is the angle that the light ray coming into the boundary makes with the normal. Then we measure the so-called reflective angle, or the angle of reflection, and that is the angle that the reflected ray makes with the normal. And then we also have the transmission angle, or the angle of refraction, and that's the angle that the refracted ray makes with the normal. All right, now it's a standard result of geometric optics that the reflective angle will always equal the angle of incidence. So these two angles are the same. All right, so what that means is that the angle between the incident ray and the reflected ray is twice the incident angle, because I got incident angle plus incident angle again. All right, the refracted angle will not be the same as the incident angle unless the speed in the two mediums is the same. And if it is, then the light can't tell the difference between the two mediums, so it might as well just be one medium, right? So in refraction, the difference between these two angles is going to depend on the difference in the two speeds. All right, now in general, this is given by Snell's law. All right, Snell's law is named after a French physicist who derived the law in 1621, despite the fact that it was known to people 600 years earlier than that. Well, history sometimes does that. All right, anyway, so Snell's law, I'm not going to talk about in detail here, but it depends on the speeds in the media. So how do we characterize the speed of light in a certain medium? Well, what we do is we define the speed as the speed of light in a vacuum divided by this number n. Now, the nice thing about this number n is that it's dimensionless. It's just a number. It doesn't have any units associated with it. So this is called the index of refraction, or sometimes people call it the refractive index, because it characterizes refraction. It allows us to calculate what this refractive angle will be. The way that I like to think about this, because I think it's really easy to remember, and it's completely correct, it works in essentially every situation, is I like to make an analogy to crowded hallways. All right, imagine you're walking through the school. If the hallway is really crowded, then that means you're not going to walk very fast. You can't. It's a crowded hallway. So when I have a large index of refraction, I have a crowded hallway, and I'll move slowly. So you can kind of think of the index of refraction as telling you how many people are in the hallway. When it's large, the hallway is crowded. When it's small, the hallway is empty, and now you're going to move much faster. All right, so we got that part of the analogy. let's talk about the Snell's law part of the analogy. If the hallway is crowded, you've got your backpack, you got your books, you got your lunch, all this stuff you're carrying, but you can't spread out and go skipping down the hallway because there's all those people in it. You've got to pull everything close into you and walk close, right? You're kind of trudging through with all the other people in the hallway. On the other hand, when you go into an empty hallway, now you can spread out. There's room for you to spread out. So let's use this analogy to discuss what happens in a situation like this one. All right, so I've got my wave coming in, and then it bends like that. All right, so I want to know the relationship between the two indices of refraction, the index in medium 1 and the index in medium 2. And I also want to know the relationship between the speeds. All right, well, I'm coming in like this, and then look, I've moved away from the normal. So what you want to think of when you see that is somebody spreading out. So this is an empty hallway. This is more crowded. So we'll say that N1 is bigger than N2 because there's more people in this hallway than in this one. And the speed is slower in region 1 than it is in region 2. Notice that bigger index, smaller speed. So it's really, really, really simple to look at that in that manner. And it's actually a lot easier if you're asked a qualitative question than it would be actually going through and using Snell's law and determining the angles. It takes too long. So if you see a light ray bend away from the normal, then that means it speeds up and the index of refraction down here is smaller. Conversely, if you were to see something come in and bend toward the normal like that, it's slowed down, it's going into a more crowded hallway, pulling itself all towards the normal, and the index of refraction is big. All right, now let's just discuss one other real simple qualitative idea that comes up but you may not have thought of. All right, suppose that I'm going to take this incident ray and I'm going to move it down like this. Well, what do you expect this ray to do? Well, geez, I mean, it's got to move away, right? I mean, I didn't change the index of refraction. So if I come down here like that, this guy's going to have to go like that. But if I keep doing that, look how much more room I got over here. I don't have any room over here. So at some point, this ray is just going to go right along the boundary. And if I try to go further than that, there can be no refracted ray. The refracted ray cannot exist. The only thing I can get is a reflected ray. This property is called total internal reflection. And it only occurs when I go from a slow-moving medium to a faster-moving medium. So you can, for example, see this phenomenon if you sit on the bottom of a 5-foot deep pool and you look up through goggles or something like that. If you look straight up, you'll see out of the water. If you look up like that a little bit, you'll see a little bit out of the water. But as you go down further and further, so that the angle that your light ray makes with the surface of the water gets too big, you suddenly won't see out anymore. You'll only see the bottom of the pool. You'll only see reflection because there can be no refraction. You can't get out into the air because the air is too much of an empty hallway and you're trying to go from water into air. Anyway, that's reflection and refraction.